Okay, today we are starting our fifth and final subtopic in class, and that is comparative biomechanics in relation to sport and athletic performance. Comparative biomechanics is a field that primarily studies non-human animals, and the comparative element here, or the term there, comparative, typically means that this is a field where we will be studying non-human animals and often using what we glean from that study to infer performance of that animal on a comparative basis. Like, for example, why is the cheetah so fast compared to other animals? Why is the gazelle such a good endurance runner compared to other animals, including humans? Just as some examples there of the type of work that's done in comparative biomechanics. This is a fascinating field to me. It's always one that I've just found intuitively intriguing and interesting. If I wasn't studying what I do in biomechanics, I'd probably try and do something in the comparative biomechanics realm. And this paper, Williams et al., 1997, Skeletal Muscle Histology and Biochemistry of an Elite Sprinter, the African Cheetah, is about not just one of my favorite subdisciplines in biomechanics, comparative biomechanics, but one of my favorite topics in comparative biomechanics, and that's the speed of the cheetah. I cover cheetahs in I think every class I teach. If you take a lot of classes with me, you probably get tired of me yammering on about cheetahs, but they're just fascinating animals to me. Here's our videos again of cheetahs in action here. A full-grown, healthy adult cheetah, men and the male and female cheetahs, to my knowledge, can reach top sprinting speeds in excess of 60 miles per hour. They've been recorded at speeds of upwards of 70 miles per hour, reaching and sustaining those speeds over short sprints for a little while. And they can go from a dead stop at zero at rest up to 60 miles per hour in about 3 seconds. They've been measured doing that. So top speeds that are over twice as fast as the best human sprinters, and acceleration that's better than most cars that humans can build, let alone humans biologically being able to do. So they're just incredible biological sprinting machines. What is it that makes them so fast? My video here paused at a fortuitous frame there, but you could see the cheetah fully stretched out. They have a massive stride length, and that's really where at least from the stride length and stride frequency thing, where their speed comes from. But let's examine this at a little bit finer level of detail in terms of what leads to the cheetah being able to take those massively long strides and cover such a long distance. Now, this paper here, Williams et al., has a variety of results in it. The one that I'm going to focus on is the fiber composition of the muscles that they measured here. Here they had data from 6 cheetahs, which is actually a very large sample size for cheetahs. There's only about maybe 7,000, maybe 8,000 cheetahs, a lot known to be alive in the world, so measuring 6 of them is pretty good in terms of a fraction of the overall population. They measured fiber type and a variety of other data on the cheetah vastus lateralis, which is a knee extensor muscle that's also present in humans, and on gastrocnemius, which is an ankle plantar flexor muscle that's also present in humans. Both muscles that are very important for sprinting in cheetahs and in humans. Now, what is our basis here for looking at these muscles and at the fiber composition of those muscles? Well, here they were interested in the fast twitch fibers of the muscles. And why there? Well, this is kind of just colloquially and intuitively what we attribute a lot of natural sprinting speed and sprinting ability to, right? Like if we see a sprinter and if we see somebody who's fast and has good sprinting ability, we tend to assume that they must have a lot of fast twitch fibers in their muscles. The fast twitch fibers tend to be the larger, more powerful muscle fibers. They can do a lot of work and can do it quickly. They tend to be the fibers that can basically outperform the slow twitch fibers for every basis of performance in muscles that is meaningful for sprinting performance. They're less efficient than the slow twitch fibers, but that doesn't really matter that much for sprinting. Sprinting, I kind of want to consume a lot of metabolic energy. My goal is mechanical power and speed. I'm not so concerned with efficiency in terms of a trade-off between work and between metabolic energy consumption. Here, I just want to go fast. And so here, having a lot of fast twitch fibers that can produce a lot of power and do a lot of work real fast on the skeleton and produce a lot of muscle force really fast is what I'm looking for here. So having a high fraction of fast twitch fibers should be something that's beneficial for sprinting speed. Is it beneficial in practice? Well, we saw some evidence there in the Miller et al. Study from 2012 when we were doing some simulations of maximum sprinting speed and manipulating the fraction of fast twitch fibers in the model's muscles. And that's what was shown here in the red squares here in this figure here with the top sprinting speeds of the model when it ran with a variety of fast twitch fiber fractions in its muscles. Clear on the left was the hypothetical case of no fast twitch fibers, which had a top speed of about 5.5 meters per second. And then clear on the right was the case of 100% fast twitch fibers in all the muscles, which was almost 7.5 meters per second. Okay? Now, those extremes are, of course, not realistic scenarios. Nobody has literally 0% or literally 100% fast twitch fibers in any single muscle, let alone in every muscle in the body. But it demonstrates the sensitivity of this performance of top sprinting speed to the range of possible fast twitch fiber fractions that you could have in your muscles. This is a huge difference in speed, 5.5 meters per second up to 7+ meters per second. If those two people raced, hypothetically, it would be a complete butt kicking. Like 7.5 meters per second would absolutely blow away 5.5 meters per second. That's a tremendous difference in sprinting speed. So even though the range of fiber types investigated here is not something that you would ever see in humans, it just demonstrates how important that fraction of fast twitch fibers in the muscles, or how sensitive performance in something like sprinting can be to even small changes, even subtle increases in fractions of fast twitch fibers there. So if that's what makes people fast or can have a big effect on speed, maybe this is what makes some animals fast. Maybe the cheetah just has a tremendous high fraction of fast twitch fibers in its muscles compared to humans, far beyond what even elite, well-trained human sprinters have. And was that the case here? You can see they note that 83% of the fibers in the vastus lateralis were fast twitch fibers, and 61% of the fibers in the gastrocnemius were fast twitch fibers in the cheetah. So here, to kind of get a sense of is that high or not, seems kind of high. Is it high in compared to humans? To get a sense for that, here I put together some results comparing the results from the study, the cheetah fast twitch fiber compositions, to a set of, here I think I had 7 studies where they measured vastus lateralis fast twitch fiber composition in human sprinters of a variety of ability levels and training levels. And the range here for the human sprinters ranged from 61% fast twitch in the vastus lateralis for a group of 3 elite human female sprinters, up to 88% was the highest average reported here for a group of 16 sub-elite male sprinters. I think these were like university level kind of national class sprinting athletes. This one here in my cell A9 there was the only one of these 7 that I found that reported like the range of the measurements in terms of what's the highest and lowest in the 6 people they measured. And here the highest one they reported was 94%. So they had at least one person in there that was quite a bit higher than the averages in the cheetahs up here. Excuse me. I have two rows here for the cheetahs because in this study they actually had 2 different types of cheetahs. They had cheetahs in captivity, who were cheetahs that were living in a zoo essentially, and also wild cheetahs that were living in the wild that they'd managed to briefly capture and do some muscle biopsies on. I should note that the cheetahs were not harmed or beyond the biopsy, which isn't the most comfortable thing in the world. But beyond that, the cheetahs were not harmed in this study. They're an endangered species. We should be nice to them and shouldn't sacrifice them when it's not necessary. And here the cheetahs were not sacrificed in this study. They were released back into the zoo or back into the wild in good health after the study was completed. So whether or not the cheetah was in captivity, where you might expect, well, it doesn't have to hunt for its own food, somebody brings its food, so maybe its muscles have atrophied a little bit, versus the cheetah being in the wild, they had a little bit higher fast twitch fiber fraction in the wild, but not dramatically higher. They're both in like the 80% range. Whereas the human sprinters, on average, if I average over all of these participants in all these studies here, had about 75% on average. So the cheetahs were a little bit higher, but not dramatically higher. Not so high that this on its own would explain like a literal doubling of the top sprinting speed in the cheetahs versus the human sprinters. And we did see some studies where the humans were comparable to the cheetahs, and some where there were humans who indeed had more fast twitch fibers than at least on average what was observed here in the cheetahs. And so it looks like vastus lateralis fast twitch fiber composition here is not unusually high in the cheetahs compared to human sprinters. For the gastrocnemius muscle, I couldn't find as much data on that for humans as I could for vastus lateralis, but there again we see a similar story, where it was 62% in the wild cheetahs. They didn't get those data in the captive cheetahs. And then in a group of 2 elite male sprinters, it was 73%, and 2 elite female sprinters, 77%. So again, here a story where, yeah, it's high in the African cheetahs, but not high compared to human sprinters. The cheetahs aren't blowing the humans away here in fast twitch fibers. For this muscle, they're actually a little bit lower. So what is it that makes the cheetah so fast? Is it its fiber type? I think we can rule that out here, that the cheetah does not seem to have unusually high fractions of fast twitch fibers. And if you look at other related characteristics of cheetah muscular performance, like there's studies on how much power their muscle fibers can generate, and they're also remarkably normal compared to other animals or compared to humans that have a high fast twitch fiber composition. So a cheetah's muscles, despite their abnormal sprinting speed, are surprisingly normal compared to faster, less effective sprinters, animals and humans that can reach much slower top sprinting speeds. Muscular properties are relatively similar there between cheetahs and between those other animals, including humans. So what is it that makes them so fast? Well, biomechanically, what this fiber type finding lets us kind of rule out is that it's not from stride frequency. Okay? And let's revisit our video here. This is something I talked about way back on like the first day of class. Let's focus on the cheetah on the left here, which was being filmed in real time. You can see the background here blurring by. That's a couple reasons for that. It's not in focus, but it's also the cheetah's moving really, really fast here. He's going at a fast top speed. He's either, to go at that fast top speed, he's either having a tremendous stride length or a tremendous stride frequency. Stride length is hard to glean from something like this, but we can get kind of a ballpark estimate of stride frequency. So let's just watch the clock up here. Watch the seconds tick by. 1001, 1002, 1003, 1004. And then let's count how frequently cheetah is completing strides here. Stride, 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 stride. So I estimate there that the cheetah is doing in the ballpark of like 2 strides per second, or a 2 hertz stride frequency. And if you think back to some of the studies we looked at on stride length, stride frequency, and human running, that's a pretty normal stride frequency for top human sprinting speed, where a human might reach, if they're really fast, might reach like 25, 30 miles per hour. Cheetah here's probably reaching 60 to 70 miles per hour. So roughly a 2-fold difference in speed, cheetah versus human, but roughly the same stride frequency, cheetah versus human. So since it's not stride frequency that's doubling the speed, by process of elimination, it is stride length. And that is indeed where, at least biomechanically, the cheetah's speed comes from. They cover a tremendous distance here with each stride they take, even though they're cycling their legs at a relatively normal rate, because all of their kind of speed and their stride frequency, power-related metrics of their muscles are roughly the same compared to human sprinters. Notice here, and if we want to get an idea of, okay, if it's not stride frequency and it's stride length, well, what is allowing them to cover such a tremendous stride length? I don't know for sure, but I speculate that it has something to do with this action of the spine that you're seeing here. Notice how much their spine is flexing and extending there while they're sprinting. This is by having such a flexible, compliant spine, that's partly allowing them to just really stretch out there at the end of their stride and just cover such a long distance. And I would also speculate there might be some serious storage and return of elastic energy going on there inside of their spine in the direction of progression here where they're heading, which is not something a human is probably going to be having with normal human sprinting form. There's, of course, other animals that have this overall shape to them in terms of 4 legs and a spine that kind of compresses and extends in the direction of progression there. But that alone will not make you fast, right? Like you guys have all seen in some of the videos here, my bigger dog, Sam, the big black-haired dog. He's a great dog for a lot of reasons, but he is not a great athlete. I could absolutely smoke him in any sprint, despite him having a flexible spine here and 4 legs, where I've just got 2 legs and don't have the flexible spine. So it's not just the 4 legs and the spine that makes you fast. It's something other here that's special about the cheetah, or some extreme ability here to really stretch out the spine and really store some energy in the spine there. Again, I don't know for sure if that's mechanically where the cheetah's speed is coming from, if that's the main thing that makes them so fast here, but I think it probably is a big factor here in terms of how fast they're able to go. Other fascinating thing here is if you look at the cheetah on the right, look how stable his head is. It is like rock steady, despite him moving along here at 60-ish miles per hour. That's pretty amazing that they're able to do that. Again, I don't know if that's why they're fast, if that contributes to it, but just something remarkable about these animals here. They're just really an impressive animal in a lot of different ways. Okay, a couple other relevant topics here to cover before we wrap it up here. What about the influence of training, and related to that, the influence of performing like this under circumstances of stress and duress and survival? Influence of training here. Cheetahs have to sprint every day, and it relates to their survival. They don't really train, like I don't think they go out and just practice sprinting for the sake of getting good at it. Maybe there's like a period where like maybe the baby cheetah cub gets some training from the mama or from the daddy cheetah to learn how to sprint fast or something. I don't really know if cheetahs do that or not, but hypothetically they might do that for like a young cheetah. But I don't think they really like go out and like train specifically to get fast like a human does. It's just kind of part of a cheetah's natural lifestyle. But could training, or could the need to sprint/run every day like a cheetah has to, could this dramatically influence things like fiber type and human sprinting performance? Of course, training for sprinting is a great way to get faster and get better at sprints. Is it because of training-induced adaptations to fiber types? This could have a small effect, but I don't know if it has a dramatic effect. This model that we use here in biomechanics and in motor control to some extent, where we have kind of two types of muscle fibers, fast and slow. That's by far the simplest model of partitioning out like what types of muscle fibers there are. In exercise physiology, you almost always see three types at least, where you have the slow oxidative fibers. These are like your endurance, marathon type fibers. You have your fast oxidative fibers, which are kind of your intermediate ones. And then you have your fast anaerobic or fast glycolytic fibers, which are your real fast ones. That's probably the next simplest model up here. There's other models that have like 9 to 12 different categories of muscle fibers that are all pretty far over my head. But kind of this model of just having two of them is fairly limited in scope, and is something we use in biomechanics just because it's simple, but most physiologists would probably find it pretty unsatisfactory. Typically in the physiology realm, you'll see at least three categories of muscle fibers. The amount of slow oxidative fibers that you have, you're pretty much stuck with. That's largely a quote-unquote genetic thing. The amount of fast glycolytic ones you have, again, you're also kind of stuck with that for largely genetic reasons. Training doesn't affect it that much. These ones in the middle, these fast oxidative fibers, those are the ones that it seems like you can shift them a little bit to one extreme or the other. Like you can make them more, you can make them more like the fast glycolytic fibers in terms of their performance abilities by doing kind of anaerobic, explosive power sprint type training. Or you can shift them to be more like the slow oxidative fibers in terms of their performance characteristics by doing slower, longer distance, endurance, aerobic, economy type training. So these ones in the middle, we can indeed affect how much of them are like faster type fibers or like slower type fibers by training. But that amount of shift you can get from that, even from like long-term extreme training, is pretty small. You're not really going to make a dramatic difference in the composition or overall composition of your muscle fibers with training. So to the extent that this is possible to shift your fiber type with training, you can do it, but I don't think it's big enough in terms of how large it's happening in terms of magnitude of that shift to really explain any dramatic differences in something like sprinting speed. More related to this notion of training is this last topic I'll bring up here in terms of the influence of stress and survival. Not that competing as a pro athlete or as a high-level sprinter or high-level athlete in any sport isn't stressful and difficult and challenging. It can be very stressful and difficult and challenging. We tend to, I think, kind of have this viewpoint that like, oh, pro athletes have it easy and it's a very relaxed, like very comfortable lifestyle. It's not a lot of the time. It can be, you often get paid fairly well for your performance, but you often don't, especially in running as a pro sport. And it's often not the most financially lucrative thing in the world, and you're often beating your body down to the point of just being on the threshold of injury, and then pushing yourself physically really, really hard, and often just making barely enough to scrape by. So it's not always the most financially lucrative endeavor in the world in terms of pro sports. They put a tremendous amount of effort and a tremendous amount of work in over a lot of years, and very few of them are independently wealthy because of it. So not to say that it's easy or that it's not difficult. It can be difficult, and it certainly isn't easy to compete at that level. But generally, your survival is not on the line every day. Your livelihood, your financial success could be on the line, but a poor performance is not going to have consequences in terms of literally living for the rest of the day. That is very much not the case in the rest of the animal kingdom. Humans, it's been many, many generations of humans living as a species on Earth, past the point of when we've needed to depend on our physical physical performance and physical prowess to literally survive every day. We don't really have to do that as modern humans, and it's been a long time, many, many generations of humans since that's been the case. In the rest of the animal kingdom, that is very much not the case. A cheetah, if it is not able to successfully find and track down and capture prey, it will not survive very long. It has to do that literally every day of its life, or it won't eat. It won't have the calories and the energy it needs to survive. Its cubs will not have the energy that they need to survive, and that cheetah's genetic line will be extinguished. And so if the cheetah wants to live, it has to sprint. It's literally life and death. I bring this up because it's going to be a theme here throughout this section in class on explaining why animals athletically seem to outperform humans a lot of the time, even if they're similar in size to a human, and even if they seem to have relatively normal muscles compared to a human. The factor that we often leave out there, I think, is the ability to truly, fully, maximally activate your muscles. We often test this in humans, and some of you may have done this on machines in the lab called dynamometers. Or if you took Kines 300, you did a lab where we used a machine called a Biodex. It's this chair that you sit in, and we strap your knee in, and we tell you, activate your quadriceps as hard as you can, and we measure some data on that for one of the labs in Kines 300. I've done that many times, and some of you have probably done it. And I don't know about you guys, but when I do it and I'm told, okay, fully activate your muscles, all you got, max isometric contraction, I just don't feel like I'm doing it. Right? It just doesn't seem like I'm truly, fully getting the most out of my muscles that I possibly could. And I think it's related to what I said there about that's not really something humans have to do very often. It's not part of our life. It's not part of our survival. It's been certainly centuries, maybe thousands of years, maybe millions of years since humans have really had to do that every day on a frequent basis. Probably not millions of years. I'm probably exaggerated there, but it's certainly been centuries since humans and many generations of human life on Earth since we've had to truly, fully activate our muscles to literally live or die on a daily basis. That's just not something humans have to do, and I often wonder if we're even able to do it like on command in laboratory situations. I'm not sure we can. Whereas animals, they have to perform at their best as they possibly can, literally every day to survive. And so maybe when we observe a cheetah running at 60, 70 miles per hour, they're not just doing it for fun. They're not just doing it because, hey, I'm on video, this will be cool. They're doing it because they want to live, because they have to do that to survive. And so I think cheetahs in particular, but I think most animals other than humans in general are a lot better at humans at fully activating their muscles, at literally producing as much force and as much power as those muscles are physically capable of, because there's the stress of needing to do that for survival, which is largely absent in modern human society for quite a long time. Okay, that is it for today. We will see you next time for more animal biomechanics.